Okay, we'll get started. Is my screen visible? It is. Sorry.
Sir, when we submit
Okay. Yeah. So yesterday we were discussing about the effect of intensity of light on the photoelectric effect. I hope there is no doubt in it. Do you have any doubt? No? Sure. So what is intensity? The amount of power radiated per unit area is called as intensity. So the next concept that we are going to see is effect of potential. You're going to see the effect of potential on the photoelectric current. Effect of potential on the photoelectric current. The previous class I told you, right? What are the three parameters associated with which we'll find intensity, frequency, and stopping potential? V naught, right? So when you're trying to find the variation of one with respect to another, right? Out of the three parameters, two will be kept constant, one will be variable. So here, if you see, we are trying to find the effect of potential. Here, when I say potential, right, I didn't use the word potential difference. I use the word potential. Potential of whom? Potential is defined only for one material. Potential difference is defined between two materials. So when you observe in yesterday's diagram, you would have observed that anode was given a positive charge. That is, the collector plate was given a positive charge. Right? Means if I am able to change what? The amount of positive charge which is present on the anode, I will be able to observe a variation occurring in the value of photoelectric current. Listen to this very carefully. Listen to this carefully. Sanjeev, any doubt? No, right? So if you want, you can recollect the diagram. One point you would have observed is the collector plate has, the emitter plate has negative charge, and the collector plate is given a positive charge because it needs to attract the electrons, right? So if you keep increasing the value of anode potential, and I'm saying, listen to my statement, I'm using the word that my photoelectric current will vary. I don't know whether it is going to increase or decrease. That's what we need to use the logic and answer, right? So if the value of anode potential is increased, I repeat, if it is increased, what will happen to the potential? What will happen to the photoelectric current? What will happen? Will it increase or decrease? Why? Because for the amount of intensity that was falling on the emitter plate, there would have been certain number of electrons that got ejected out. But not all the electrons will have sufficient amount of energy to reach the anode, to reach the collector plate. So what are you doing to the collector plate? Artificially, you are making it more powerful by making it more positive, so that it can pull the weak electrons also towards itself. As a result of which, we can say that there is definitely going to be an increase in the value of anode. Increase in the value of photoelectric current. So when you draw the graph, right, observe this carefully, okay? When you draw the graph, in yesterday's graph, observe, when you drew the graph with respect to intensity, where did we start the graph with? By intensity can be zero. When? Photoelectric current is dependent on intensity. When light itself is not there, when there is no light, intensity is zero. So there is a possibility of you creating a zero intensity situation. But in this case, what are you doing? In this case, what are you doing? You are actually making the intensity constant. If you make the intensity itself zero, you start from zero, then what will happen? There, irrespective of whether you increase the anode potential or not, nothing is going to happen. It will sit idle only. So when there is a sufficient amount of intensity already present, this graph will not start from zero, rather it will start from here. It is increased. First thing is, for the electrons to get ejected out, you need light. So there can be no concept where you're saying intensity of light is zero, that is darkness. It has nothing to do with intensity, because on the y-axis it is not intensity, it is photocurrent. Photoelectric current is not zero. When the anode potential, even when you make the anode potential zero, photoelectric current need not be zero. Why? Because there is already some intensity which has pulled the electrons out. The only thing is, you are actually trying to increase the number of photoelectrons attraction by increasing the anode potential. So the graph starts from here, but it is not like you will have so much of variation. It is not like you're going to have so much of variation. There will be a slight increase in the value of photoelectric current as the anode potential is increasing. After a point, it will attain saturation. It will attain saturation. Similarly, if I increase the intensity of the same light, I'm not changing the frequency. I'm increasing the intensity, but throughout the experimental process, I'm keeping the intensity constant. So let's say this intensity is I1. So here, not to get confused, I stands for intensity, not current. Okay. Now my question is, if I increase the intensity, where will the second graph start from? Will it start from, observe this carefully, listen to my question. Okay. Is it going to start from the same point, or is it going to start slightly above this? It will be slightly above this, because even when the anode potential is zero, since there is some amount of intensity which was greater than the previous case existing, there will be slightly more amount of photocurrent existing. So the graph will start slightly above. Right? So it will start slightly above and it will go in this way. Again, the same saturation will be attained. So what does this graph tell us on the positive side? What does this graph have to tell us on the positive side? It says that as the intensity is increasing, even at zero anode potential, my value of photoelectric current will be slightly high. Okay. But after a certain point, it will attain saturation. So as the intensity keeps increasing, the initial value of my photoelectric current will also keep increasing. But here comes the question. When I told effect of potential, I told anode is given a positive potential. Okay. Why do you give positive potential only to attract more electrons? Now I have a question. Can I give a negative potential also to it? How to? But that's what I'm doing. Electrons, I'm not concerned. I'm not concerned. So if I here, I'm not concerned about photoelectric current increase. I'm only doing a testing of understanding how much strength does an electron have to overcome the repulsion to itself. So I already did my supporting process by giving it a positive charge. If I give the anode a negative charge, what am I trying to do? I'm trying to test the strength or the energy that the electron has to reach the collector plate by overcoming the repulsion. Right? So what will happen? As I keep increasing the anode potential in the positive direction, which I call it as an accelerating potential, because it is accelerating the electrons. That's what they call it as anode potential when you apply it in this direction. Whereas if you apply the same anode potential but with a negative value in the left-hand direction, what are you doing? You're actually applying retarding potential. So when it is retarding potential, what will happen is the intensity, though it is constant, the amount of photoelectric current will increase, but there will be one particular value of anode potential in the negative direction, which will completely stop the electron from reaching it. Makes sense? You're able to understand what I'm trying to say? So here, if I say I'm giving a negative charge of -1 volt, yes, 2 electrons are able to reach. Okay, I'll make it as 5. I'll make it as -2 volt. Then let's say out of 5, 2 have given up. Only 3 are able to reach. Now I increased it to -3. Out of 3, 2 are given up. Only 1 is able to reach. When I take it to -4, that 1 also gave up. And it is also not. So that was the one with the highest energy. So even that was not able to reach. So you are able to apply a negative potential. So what are you doing? You are applying the negative potential, which is completely stopping the electrons from reaching the collector plate, and that negative potential is what is called as stopping potential, because it's stopping. Okay, so one point that you need to make a note of is during the saturation current, at the stage when the saturation current is obtained, what is going to happen? All the electrons emitted by the collector plate are completely collected by the all the electrons emitted by the emitter plate are completely collected by the collector plate. That's it. There is no deviation. There is a when you say they will go back, yeah, that can also happen. There is completely theoretical distribution. And as we see, we can't say. But theoretically, you can say it can be a equilibrium when this energy and this energy are equal. Actually, I do it bad actually. It's not a straight line. It should actually take a bend like this. But one point if you observe, how much ever you increase the intensity, you can increase the saturation current, but stopping potential is the same. Is that clear? So questions will be based on this only one intensity, which is what we have to stopping potential will change or not. But intensity increases, photoelectric current will increase by because the number of electrons per second are increasing. Charge of electrons which are positive. Positive charge rather it becomes more positive. It is neutral, it will become positive. However, you take all the three scenarios, it is going to be positive. That's the statement given. Okay. So it's the same theory which I explained. Right? I explained the points already. Now the point is, I need to frame a mathematical equation to understand what would be the value of my stopping potential. For that, what I will do is, there will be an electron which has maximum kinetic energy. Is that right? So the maximum kinetic energy can be written as half into m into V max square. So who is giving it maximum kinetic energy? It is the velocity with which it comes. Because mass of all the electrons are same. Correct? So this will be equal to E into V naught, where V naught is what is called as the stopping potential. So what we are trying to say is, when you apply the work energy theorem, work done by the stopping potential is equal to the change in kinetic energy. Everybody knows work energy theorem, right? Work done by all the forces will be equal to the change in kinetic energy. That's what you need to do. Is it clear? Okay. So if you repeat the experiment with the incident radiation of the same frequency but of higher intensity, we find that the value of saturation current is increased in proportion to the intensity of the incident radiation, while the stopping potential still remains the same. So what can you say? Thus, for a given frequency of incident radiation, stopping potential is independent of intensity. So from this, you can also conclude that the maximum kinetic energy of the photoelectrons is also independent of the intensity. These two are often asked questions. And the last experimental study is effect of frequency of the incident radiation on stopping potential. So the third parameter, that is frequency, is varied, keeping the intensity constant. Can we do that? I'm changing the frequency, but I'm keeping intensity constant. How is it possible? For example, if this is a plate on which you are making a red color light incident, okay, on the same plate I am making an yellow light incident. So what have I changed? I've changed the frequency. The wavelength, obviously I've changed the frequency also, but I can still make the amount of power radiated per unit area to be constant. See, nothing. You have a wall, let's say on the wall light is falling and you have a bright spot. I can keep that bright spot constant whether I use red light or an yellow light. I can adjust it in such a way that the intensity is kept constant. But what are you changing? You're changing the frequency itself when you're doing it. Okay. To study the effect of frequency on the photoelectric effect, the intensity of the incident radiation at each frequency is adjusted in such a way that the saturation current is same each time when the plate A is of positive potential. 1 minute. After this, content is not there. ஒரே நிமிஷம் have to bring the content. Can't drop this good notes. So effect of frequency of incident radiation on stopping potential. Okay. So what you're doing is keeping the photosensitive plate C and intensity of incident radiation constant. You're observing the effect of incident radiations on stopping potential. So when you do this, you can observe that the saturation current is there now. As you keep increasing the anode potential, since there is certain amount of intensity which is kept constant. Okay. So due to that intensity, there will be some photoelectric current existing. And here also you have, and here also you have. Okay. Thank you. Whereas when you start applying the potential in the reverse direction, it becomes minus V naught. Okay. And here it is minus V naught 2, and here it is minus V naught 3. Okay. So what is the difference between previous graph and this graph? There is intensity when you increase it. What was happening? Saturation current also increased in the same proportion. Whereas here, what is happening? The intensity, since you are keeping it constant, depending on frequency, one important change is occurring compared to the previous. Stopping potential is also increasing. That is the same thing. So when is saturation set to be attained? When there is no more effect possible. That is when you say saturation has occurred. But the question that we need to answer is why? How is the frequency able to increase the amount of stopping potential? So here I have written it also. You know that E is equal to h nu, right? And when you equate that h nu to kinetic energy, so that h nu will in turn produce an electron with maximum kinetic energy. And that maximum kinetic energy is mathematically equal to E into V naught. Okay. Shall I proceed? So from here, there are certain, one minute, I'll do one thing. I'll try to open it in another app so that I can write it again. I don't know, Pakram. Okay, but it's fine. It's okay, right? You guys are not getting disturbed with already written content. Okay. So So here, make an important note. From here, the mathematical aspect will come into picture. If the frequency of incident radiation is plotted against the corresponding stopping potential, then a straight line is obtained as shown in the figure. Okay. First draw the graph, then we'll start thinking of the logic. Did you draw it? Okay. Now see. How do I open new note graph? So let's say this is the photosensitive plate onto which there is an incident radiation made to form. Okay. So the radiation has an energy h nu. So this h nu has to overcome two things. What is it? One is it has to overcome the work function. So once it overcomes the work function, it needs to give maximum kinetic energy to the electron. So can I write it as half m into b max so that it escapes the nuclear pull? Is that right? So can I write h nu is equal to h into nu naught plus in the place of half m v max square, can I write it as e v naught? So E into V naught will be equal to h nu minus h nu naught. So what is the value of V naught that I can write? H divided by E into nu minus h divided by E into nu naught. Can I do this? So what is the graph that you drew? The graph that we drew was showing the variation of V naught and nu. So if V naught is taken as y, is it not of the form y is equal to mx plus c? But c is having a negative value. Is it right? So this value is called as the threshold frequency. Is it clear? So this is called as a threshold frequency, and if I take this to be theta, then tan theta is what is slope, and slope is given as h divided by e. Is it clear? Now we need, you want to copy that? Shall we proceed? Now listen. The next concept is laws of photoelectric emission. So what we did is we experimentally observed the pattern of photoelectric effect, and the observation are and those observations are framed into the fundamental laws of photoelectric emission. Just give me a minute. Right. So the first thing is, for a given photosensitive material, first listen to then you can write it. Just have an observation. For a given photosensitive material, what material is that? I'm talking about the emitter plate. For a given photosensitive material, there is a minimum frequency which is required, below which photoelectric emission is not possible. What is that minimum frequency called as? It's called threshold frequency. Similarly, for a given photosensitive material, the photoelectric current is directly proportional to whom? Number of photons per second, that is intensity, basically intensity. So photoelectric current is directly proportional to the intensity, provided the frequency is greater than the threshold frequency. Adillama, you cannot say directly proportional to intensity. Third, this is what I told you yesterday. Photoelectric emission is an instantaneous process. That is, there is absolutely no time lag between the incidence of radiation and the emission of photoelectrons. As soon as the radiation is false, greater than the threshold frequency, the emission takes place. Generally, it happens in 10 power minus 9 seconds or 1 nanosecond. It happens in 1 nanosecond, okay? And the last point is, the maximum kinetic energy of the photoelectron is directly proportional to the frequency of the incident radiation, but it is independent of intensity. Because what did we say maximum kinetic energy is? E into V naught. So kinetic energy is dependent on stopping potential. Stopping potential does not depend on the intensity. These are all the important observations which were seen in the experimental aspect, and they framed it as laws. That is why the heading is called as laws of photoelectric emission. Am I clear? How we can make it? So when you're writing, as far as possible, don't look at the board. Just read the statement, write it on your own. Go one by one. Because if you see the previous graph, what was the graph? It's stopping potential and frequency. What was the graph? Straight line. Stopping potential and frequency. Straight line. Straight line is something like here. Finished. You finished. Now, based on this, we need to know what are light waves and photons. Okay. So, light waves basically came from the concept of electromagnetic theory, which was proposed by Maxwell. So, wave theory could not explain the concept of photoelectric effect, but Planck's equation, Max Planck's quantum theory, successfully explains photoelectric effect. So, what is the theory according to Planck? So, according to Planck's quantum theory, light is basically not going to travel in the form of a wave, rather it is emitted in the form of small packets called quanta or photon. Okay. Then each photon, each packet of that sort has an energy associated with it whose value is equal to h nu, where h is called as the Planck's constant and its value is 6.626 into 10 power minus 34 joules second. Okay. Next is photon. When you talk about it, is neither a particle nor a wave. Okay, because it has dual nature. Photon basically light only. Right. So in the phenomena like interference, diffraction, and polarization, photon behaves like a wave, whereas the phenomenon of emission, absorption, and interaction with matter, that is a photoelectric effect, photon behaves as a particle. Hence, light photon has dual nature associated. That's the point. This is what happened. This is what gave rise to the concept of dual nature of matter. Most importantly, dual nature of radiation in this context. Clear? See, this point I hope you have got this in your mind. Right? You want to copy this? Yeah, please. Shall I proceed? Yeah. Done. So this gives rise to the concept of Einstein's photoelectric equation, which I've already given it to you. So here I explain, no? H nu is equal to W naught plus half mv max square. This is what is called as Einstein's photoelectric equation. So let's try to dissect this equation and understand. Okay. First, what is H nu? That is the energy of each photon, according to Planck's theory. So the energy associated with each photon is utilized partially to overcome the work function of the matter. What do we mean by work function? It needs to overcome the minimum energy that it needs for the electron to escape. So it doesn't stop with the fact that the electron has escaped. The escaped electron is supposed to have maximum kinetic energy so that it is not being pulled back by the nucleus. So that is why if you see this equation says the energy of each photon is utilized to overcome the work function and provided maximum kinetic energy to the photoelectron. Is that point clear? And that's what is given in this whole story. Okay. Then experimental verification of Einstein's photoelectric equation. This also I showed it. We drew the graph, no? The graph is based on this equation. We have already given it. Other than on the graph, on the graph, left clear. Same thing. So this also I have explained. Okay. With this, 80% of the chapter is over. The next part that is left out is matter waves. Now the question is, when light can behave like a particle, can a particle behave like a wave? That is, when an electromagnetic wave can exhibit the properties of a particle, is a vice versa possible because nature follows symmetry. Right? Nature is symmetrical. Like how you can generate electricity from magnetism and magnetism from electricity. It's the same process again. Right? So what happened is, the radiant energy has dual aspects of particle and wave. Hence, a natural question arises: if radiation has dual nature, why not matter? So in 1924, what happened is French physicist named, actually pronounce it as Louis de Broglie. It is not de Broglie. Okay, it is de Broglie. D-E-B-R-O-Y. Okay. So he put forward the bold hypothesis that moving particles should possess wave-like properties under suitable conditions. He reasoned this idea from the fact that nature is symmetrical and hence the basic entities like matter and energy should have symmetrical characteristics. Okay. So what he's saying is, if radiation has dual aspects, matter will also have dual aspect. And when was it proposed? In the year 1924. So almost 98 years back. 2 years, 100 years. 2022. Huh? Right. So his theory is something like this. Since he told the matter possesses wave-like properties, the first important parameter for a wave is wavelength. Correct? Wave nala wavelength. You cannot talk it for an oscillation. So de Broglie's wavelength of matter waves. So what he did is, he took the idea of Planck's equation. What does Planck's equation tell you? Energy of each photon is h nu, and he combined it with Einstein's energy mass equivalent relationship, which is E is equal to mc square. So when you equate both, hc by lambda, can I write it as mc square? C and c will get cancelled, which implies lambda is equal to h divided by m into c. Lambda is equal to h by m into c, where h is Planck's constant, it is mass of the charged particle, and what does C stand for? Speed. So mass into velocity is called as linear momentum, h divided by p. See, from here only that Heisenberg's uncertainty principle, everything comes into picture. Okay, but before that, the basic is matter has a wavelength property which says lambda is equal to h divided by mv, and this is called as whose wavelength? Obviously, you know this, right? You know this equation. So it's called De Broglie's wavelength. De Broglie na yung ishtam. அப்படிதான் படிச்சனா அப்படி படிப்பேன். Then the 11th standard atomic structure, chemistry. Another Heisenberg's uncertainty principle. Okay, and one more equation that you can write is lambda is equal to h by p or h by root of 2m into k, because linear momentum is root of 2 times mass into kinetic energy, or you can write it as, okay, that's it. Is that clear? Kinetic energy. Because kinetic energy is p square by 2m. K is equal to p square by 2m. So p square is equal to 2m into k. P will be root of 2m into k. Okay. So using the same logic, if you want to derive an expression for De Broglie's wavelength of an electron, so there it was told for matter waves. So that's why De Broglie wavelength for matter waves. Here, if you are specific that you want to derive it for an electron, what you can do is, first is you take a positive and a negative potential and make the electron get translated from the negative to the positive potential, where there is a potential difference of V volt applied. So what is the energy you are giving to the photon? Sorry, electron. Energy is E into V. This energy will get converted to kinetic energy, half mv square. Right? But V, how can you write it as? Or I can make it even more simple. Since kinetic energy is E into V, we know that lambda is equal to h divided by mv. mv equal root of, so h divided by root of 2m into ev in direct opposite. Where E is the charge of electron and V is the potential difference across which the electron is made to travel. Is that clear? So when you substitute all the values of h, m, e and everything and calculate, right, you will get the wavelength as 12.27 divided by root v angstrom. And this you can use it in problems. 12.27 divided by square root of v angstrom. Am I clear? Shall I proceed? Yeah, if at all you want to draw the graph between lambda and v. Actually, you will not draw it between v, you will draw it for root v. So you can observe that lambda is inversely proportional to root v for an electron, where v is the potential across which it is accelerated. So lambda decreases with the increase in the value of root v. That's it. Okay. And the last concept of this chapter is wave mechanical concept of an atom. So what did De Broglie say? He told that the electron of mass m in motion with the velocity v is associated with wave whose wavelength is lambda. And how is lambda given as? Lambda is equal to h divided by m into v. On the basis of De Broglie's hypothesis, an atom model was proposed in which stationary orbits of Bohr's model were retained. So what happens is, if this is the electron, which was revolving in an orbit, but now how is it moving? It is moving in a wave-like structure, right? You know what is one wavelength, right? It is the length of one wave, basically. I'm not talking about the distance between crest and drum or something. Length of one wave is wavelength. So if an electron has started here and it has to come back to the same point, then it should complete integral number of wavelengths. So n times lambda should be equal to 2 into pi into Rn, where n is the radius of the nth orbit. Rn is the radius of the nth orbit. So n into h divided by mv is equal to 2 pi into Rn. So nh divided by 2 pi is equal to m into v into Rn. What is this? M into v into Rn is angular momentum. Nh by 2 pi is quantization of angular momentum. Where else did we see this equation? So in the 5th chapter, when we discussed about the atoms dipole moment, we got a concept called as Bohr magneton, one of the derivations. Then we used it. The first derivation of 5th chapter. Is that clear? Shall I proceed? Did you understand the equation? So L is equal to NH by 2 pi, and that's it. And the last point is failure of why did wave theory fail for photoelectric effect? This is an often asked question. If you have to see from exam perspective, it's a 3-mark question. Okay, write it down. So according to wave theory of light, what should have happened? According to wave theory, the free electrons at the surface would have absorbed the radiant energy continuously. They would have not come out. They would have kept on continuously absorbing the energy. Okay. Secondly, the greater the intensity of radiation. So we know this fact that the intensity is directly proportional to amplitude square. So greater the intensity of radiation, what should have happened? Greater the amplitude of the electric and magnetic fields. Consequently, greater the intensity, greater should be the energy absorbed by the electron. But what are we saying? It is independent of intensity in a problem. According to photoelectric effect theory, you're saying the stopping potential and the maximum kinetic energy of photoelectrons are independent of intensity. But had wave theory poked its nose into it, then you should have used the explanation with respect to amplitude and then explained. This didn't work. So what is the expectation? In this picture, maximum kinetic energy of the photoelectrons on the surface is then expected to increase with intensity. But what is happening? Nothing is happening. It is constant. Is that clear? So this concept is there in NCERT also. There are 3 points given. Same thing. One more point is, the third point that they will say is photoelectric effect is an instantaneous process. So I told you, this is asked for 3 marks. So third point, one the other. Okay. So this is something I prepared. I suggest you to read the concept from NCERT also. Either this part of it. Why wave theory failed. To explain the photoelectric effect, read it from NCERT. And with this chapter is over. As I told you, these are all very small chapters. I didn't even see which is deleted or which is there. I taught everything. So it's better you also study everything. Okay. Similarly, atoms is also a small chapter. Atoms, nuclei, semiconductors. Mostly done. Okay. So one update is next week I'm not there. Okay. But I'm going to give you 2 days study holiday, and 1 day I want to utilize for test. Test not from second volume, it is from the first volume which I have already written your school also. First 3 chapters. First 3 chapters I want you to prepare, and this time it is not going to be for 35, it is going to be for 70. 3 hours. Okay. So Monday, Tuesday, you'll have study holidays. Wednesday, you'll have it. Timing on the 5 to 8 plan because you are the customer. So Wednesday, I'm planning from 5 to 8. So you don't cover 6:30 or 9:30. I know staff can't stay here. They can be write it from home. But bring your papers and give it. But write it sincere. Bring your papers, give it here. Whatever you know, right? Only then I can tell you. Sorry. So 5, I know you can't surely come. Correct? So if you can't come, write it down. But does take paper. Correct. But I want to finish it off next week. I want to start the test for these chapters. These 4 chapters put together on 22 marks weightage. You can easily score. What exam? Either next 4 chapter, I think 24, 22 or 18, or something like that. This volume you can actually score well. Ray optics and wave optics 17. Is somewhere around 20 or 22. Second volume, the weightage, I think. First volume comes somewhere. Problems from first volume.
Sir,
Tell me.
sir, when will we have a test for EMI?
I'm not able to hear.
When will we have a tap test for EMI?
Yes, sir.
Yes, sir, for electromagnetic induction.
Yeah, you'll have it. You'll have it. Don't worry. Once the syllabus is over, you have to write only tests.
Okay, sir.
You'll have it. So you can expect me to complete it by October 1st week itself. October 1st week syllabus most of it. Then I'll give you maybe 1 or 2 weeks. I'll give you time to study. Yes. Okay. That's it. Okay, go and revise this chapter. So as I told you, next week on the test. If you're done, you can leave.